Thank you very much. I already gave the same talk at some conferences, and some of you already know this subject, so I'm sorry for that. Let F and G be two new forms of weights K and L, and respective levels and F and then G. So just to, because I will need this notation, let denote by A and F and A and G the Fourier coefficients of expansions of these modular forms at infinity. So Tilouine is associated to each new form a p-adic representation of the global Galois group so we have a p-adic representation for F and for G. Which are two-dimensional. Over some finite extension of QP. And the L functions of these representations coincide with L functions associated to F and G. The main object of this talk is the tensor product of these representations. So it's a complex L function has the analytic counterpart, which is the Rankin-Selberg L-function. And they coincide up to some finite number of factors at bad reduction primes, but it is not so serious and so important. Okay, so let's assume that K and L are both bigger than 2 and that K is bigger than or equal to L. So let's look the behavior of Rankin-Selberg L function. Here we have 0. This is the value of S. L minus 1, L, K plus L minus 1 by 2, and K. So K plus L minus 1 by 2 is critical strip of, for this function. Sorry, stupid thing. So it's the central point. Central point. The critical strip is the interval between L and k minus 1. Next, if you accept the central point, the order of vanishing of the complex L function is 0 at the critical strip. Here, the order of vanishing is 1, and here it is 2. And here it is 0. Yeah? So if we have an integer g between L and k minus 1, it is in a critical strip, and we have the following rationality property of a L function. So if we divide its value at g by the period, which is here 2 pi to j minus L plus 1 Peterson square product f, it is an algebraic number. And one can try to construct the p-adic L function interpolating these special values divided by periods. To do this, let's fix a prime p which will not divide the levels, and assume this is not important for a general theory, but this will be the context we will be interested in, that k is equal to L. Yeah. So consider the AK polynomials at P of these two modular forms. Yes, exactly. But we will vary the forms, and it will not be serious. Yeah, but yeah, I just introduce some notations which will be kept till the end of the talk. Yeah. So let alpha pf and beta pf be the eigenvalues of a Q operator. The same for G. And we will make the following assumptions on till the end of this talk. So the first condition conjecturally always holds, but it is difficult. It follows from the semi-simplicity of Frobenius. And we will assume that the p-adic evaluations of alpha pf and alpha pg are strictly smaller than L minus 1. And two technical conditions. So we assume that the product of characters is different from 1 and primitive modulo nf and g, and that f is different from the dual, the form dual to g, because we want to avoid the case of a symmetric square. Yeah. Because otherwise the theory will be interesting but completely different. So Hida in the ordinary case and Coleman in general constructed families of modular forms families with respect to where x and y are the weights which vary of modular forms. Passing through the stabilizations of f and g with respect to alpha and beta, with alpha f and alpha g. And again, Hida in the ordinary case and Urban in general constructed a free variable p-adic L-function which we'll denote by LP FG XYZ S, interpolating the values of these forms in a family. So for x, y critical, so precisely we will assume that x is congruent to y congruent to k modulo p minus 1, that g is congruent to k mod p minus 1, and that J is bigger or equal to what are our conditions? Y and less or equal to x minus 1. Sorry? We assume that k is equal to L, yeah. Yeah. Yeah? Here. Here. Yeah. It's 2. Yeah. Okay, so for us, the important thing that we just take here one branch of Urban cell function, which corresponds to the value of a complex cell function at f and g, both of weight k, and g equal to k also. Otherwise, all these statements are quite technical, and I don't want to state it in a full generality. Yeah. Yeah. Just, I think it became too much involved, so I will not give so much. Sorry? Yes, yes. In theory, we should work with different branches. Yes, yeah. Here, this construction in the non-ordinary case uses essentially the work of Andriata, Iovita, and Stevens. So we have a p-adic L-function which interpolates in spatial values of complex cell functions, and we will be at least for a main result of this talk, we will consider just the restriction of this L function, which will denote LP alpha alpha. FGS, so the restriction of this Urban cell function to the case k equal to x equal to k, y equal to k, and s varies. So we get here one variable L function, p-adic L function. The point is that k is not in the critical point for the Rankin-Selberg convolution when k is equal to L. So this is a way to construct a p-adic L function at a non-critical, for the representation which has no critical points, just considering these families and constructing this function by continuity. The next results will confirm that this is a good construction. So this p-adic L function has an arithmetical meaning and the predicted properties of p-adic L function associated to forms f and g. So to do that, let's introduce some more notation. So we denote by decrease WFG the crystalline modulate P associated to this representation. So this is the tensor product of crystalline modulus associated to WF and WG. And the structure of each module is well known, thanks to the work of many people, but this is relatively old results. So this is a two-dimensional vector space generated by two eigenvectors, which I will denote by eta f alpha and eta f beta, eigenvectors corresponding to alpha and beta. And the filtration structure is given by a submodule of dimension 1, fill k minus 1 decrease WF, which has a canonical generator, which comes from geometry, so it's given by the differential form, so associated to F. And because we can do the same for a dual form, we can also canonically choose these eigenvectors eta F and in the dual, for a dual representation, so to complete also this base, okay, so get some canonical base. Yeah? Yes, this eta f alpha is the eigenvector, which is canonical, associated to alpha pf. Yeah. Yes. Yeah. 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 So, Peuin-Rion suggested an explicit formula for a behavior of p-adic L-functions in general. In non-critical points. So because normally when we construct a p-adic L-function, we interpolate the values of a complex L-function in critical points. So in critical points, with except some exceptional cases, we can easily relate complex and p-adic L-functions, but in the non-critical points, the value of L-functions is obtained by interpolation. And there is no reason a priori that this value would be related to the value of a complex L-function. And Peuin-Rion suggested that the relation, an explicit relation between complex and p-adic L-function in these cases of the following form. So I write it for our case, and we'll explain the meaning of some terms just later, just after. So this is the sum Euler-like factor, which I will precise. the value of a complex L function divided by the complex period at G and multiplied by the p-adic period of G. So morally, omega infinity comes from Deline's cohomology, and omega p comes from syndromic cohomology. So this factor is of following form. So we denote by d alpha eta f alpha tensor decrease of W G. Sorry? This one. So that's our conjecturally true, but nobody knows. But yeah. Okay. So epsilon d alpha j can be written as a determinant of 1 minus phi acting on decrease WFG. And we want to, yeah, because it should depend on J, so we twist by the cyclotomic character G times. And we quotient this decrease by d alpha, but d alpha lives here. So we also twist d alpha and consider the corresponding object here. So this is the twist of d alpha by g power of cyclotomic character, but on the crystalline side, times the determinant of 1 minus p minus 1 phi minus 1 acting on d alpha j. This is a p-adic number. So yes, but by Deline's conjecture, this quotient is algebraic in a non-critical point. Because in a critical point, this is an easy thing, and in a critical point, this involves Beilinson regulator. Yeah. So here there is a lot of conjectures inside. Yeah. So we assume Beilinson's conjecture about the rationality of this quotient, but also it becomes reasonable when we also assume that the p-adic period, or the symptomic regulator, is non-zero. Yeah, so it's not generated. So yeah, determinant is non-zero. Yeah, and this is also absolutely. So it's very difficult. Okay, so some results toward this conjecture in this case was obtained recently by Darmon Rodger and Kings, Loeffler, and Zerbez. So in the sense that for example, Kingslöffler and Zerbes, they consider this conjecture at the strip where the order of vanishing is exactly 1. And they replace Beilinson and p-adic regulators by periods of some concrete elements. So the Beilinson-Flach element. But they cannot prove that, for example, the p-adic period is non-zero. Yeah. So the question which we will consider till the end of this talk is now the following. Question. Does, assume that, maybe I will first write the following definition. So we will say that the p-adic L-function has an extra zero at S equal to J, if and only if this array-like factor vanishes at J. And therefore, p-adic L-function vanishes by some trivial reason, because this simple term vanishes. So the question is, does the derivative of this function has an arithmetical meaning? So this is a quite old question, which was studied in several cases. So for Dirichlet functions, the answer is that so it can occur only if S equal to 0 or 1, but let's consider 0. When the Dirichlet character is trivial at P and is odd. And in this case, the first derivative of a p-adic L-function can be written in the following form, where L of eta is some explicit p unit. Sorry? Yeah, but I write vaguely, yes, logarithm, yeah. Explicit p unit. And it was proved by Ferreira and Greenberg. "40 years ago. In the case of modular forms, there are two cases. So the most known case is the case of modular forms of odd weight, even weight, and level divided by P. This is a Mazur-Tate-Teitelbaum conjecture. And the derivative of the p-adic L function is related to the derivative of, to the value of a complex L function via Fontaine-Mazur L invariant. And if K is odd, so in the paper, Mazur, Tate, and Teitelbaum also mentioned this case, but at that time it was not clear how to define the L invariant, so this invariant appearing in the conjectural formula. And it was this L invariant was defined by a speaker some time ago, and the corresponding formula was proved. And also I gave some completely general definition of the L invariant. For semi-stable at P representations. Sorry? Yeah. So this means that, for representation, abstract, in some sense, abstract global Galois representations, which are semi-stable at P and satisfy some natural conjectures like Beilinson conjecture. So in all these cases, trivial zeros or extra zeros appear in the critical strip. So the case of a Rankin-Selberg L function is probably the first case where the extra zero appears in the non-critical point. So we have, in the conjectural Peuin-Rion formula, we have a p-adic regulator. So now I pass to the main result of this talk. So, Beilinson Flack and Flack constructed some special element in the global cohomology group of Q with coefficients in the p-adic representation twisted by K. And this element was included in some Euler system. And it was done by many people, so by Darmon, with Rodger, Kings, Loeffler, Zerbez, and Lai. So we have some special element in the global Galois cohomology. How many time I have? Sorry? Thank you. So what are the properties of this element? Let's consider its localizations in local Glock homology groups. So the localization lives in H1F if L doesn't divide the product of levels. This is an easy thing. This is a Bloch-Kato-Zellmer group, local Zellmer group. The most interesting thing happens if you localize at P. And it is almost true that it lives in HFQP WFG. So that's true if the product alpha PF beta PG is different from P K minus 1. And this follows from a very general argument from a quite recent paper of Nikovar and Niziol. Otherwise, if this condition doesn't hold, it lives, so we can say that it lives in the geometric part of this group. So the best that can be proved, but normally what one can expect that again it lives in H1F. We don't know. So let's consider the following map called the logarithm of Bloch-Kato, which goes from H1F, QP WFGK to the tangent space of a representation decrease WFGK quotient by field 0 decrease WFGK. So in some sense, we want to construct a p-adic period, but not as determinant, because we can never prove that the determinant is non-zero, but construct the p-adic period of this special element, so which localization conjecturally lives here. So the easiest way is to take some test vector in a dual space and to take the pairing. So we consider the representation WF star G star associated to dual modular forms. We twist it by k minus 1th power cyclotomic character. We take decrease of this representation and consider the zero filtration of this crystalline module. And inside we have the element which we denote by B F star G star, which is So we take the eigenvector with respect to the dual to alpha, so we pass to the dual representations. We have again the same decomposition, eta f star alpha star, tensor omega g star. And we should shift by k minus 1 power of a cyclotomic character, but in the crystalline module. And we get here an explicit test vector, which lives in the vector space dual to that one. And we define the p-adic period of the element of Beilinson Flag as the pairing of logarithm of Bloch-Kato of the localization of a Beilinson Flag element and this test vector. This is an element E. So now we can formulate the main result of this paper, this talk. So we keep all previous notation and assumption. In particular, we assume that f and g are of the same weight k. Then first statement, the p-adic L-function LPFGS has an extra zero if and only if at S equal to J, if and only if either S is equal to K and alpha PF beta PJ is P at K minus 1, or S equal to K minus 1, and here we can just write the dual condition of some product of eigenvalues is equal to pk minus 1, but in a dual case. So because these two cases are related by the functional equation, one can consider, for example, the case of S equal to K. Here, assume that the p-adic period of a Beilinson Flag element is non-zero. Then, indeed, the p-adic L-function vanishes in K, which is not obvious from the definition of Furban, and because it is LPFG is defined by interpolation property. So even if we say abstractly that it has an extra zero at K, this just means that some Euler, the product of some Euler like terms is zero, but this product is still not related to the value of p-adic L-function at a point. So we see that this is the case. And the derivative of this function at K can be written as the following product. So the first term is the product of some Gauss sums, which are not important, and I never can remember the exact form of them. So Gauss sums and gamma factors. Next, the second term looks almost like E in Peuin-Rion's conjecture, but E vanishes just by definition because we are in the extra zero case. So E plus is the product of non-zero linear terms in this E. Next, LFG, so some L invariant times omega p ZBF. So here LFG is some ad hoc L invariant which coincides with a general definition so I am not completely precise, but I put the most important condition because there are our one. So the most important condition is that the dimension of a global Bloch-Kator Zellmer group is as predicted by Beilanson's conjecture. Beilanson's conjecture, yeah. There is no Archimedean L value, but for Rankin-Selberg L-functions, the quotient of Archimedean value by Archimedean period is just some explicit number. So we can write completely explicitly the formula for this quotient, and we can incorporate it. Maybe some terms will cancel here, and we get exactly the predicted relation between complex and p-adic L-functions. So we cannot use the general definition of L invariant here because we don't know if a Beilanson, for example, Beilanson conjecture holds or not holds in this case. So the definition is in some sense ad hoc, but looks like the general. Also, if we assume that this function, p-adic L-function, doesn't vanish at k, so just this L invariant disappears, E plus coincides with E, and we get the formula of Darmon, Rodger, Kingslöffler, and Zerbes. No, if omega p is 0, we have problem with we have problem to connect the L invariant to the dual exponential map. We can show that the derivative is 0, but at the point 2, we have problems. Yes, but I agree, yeah. How much time? 5 minutes. Okay. I prefer to stop here, and if there are some questions, I will respond.